Logic gates. I'm Ira Goldstein. Logic gates perform basic operations on electrical signals. The electrical signals we can think of as being on or off, or being a 1 or a 0. Logic gates have one or more inputs, but they will have one and only one output. Gates are combined to make circuits. Logic gates can be represented as Boolean expressions, which look like algebra. In this case, x is equal to a and b. They can be represented by logic diagrams. Logic diagrams are black and white drawings where gates are distinguished only by their shape. Or they can be truth tables, which list all the possible input values and their corresponding output values. A logic gate can be represented, as I said, by a Boolean expression, a diagram, or a truth table. We will learn how to convert between Boolean expressions, logic diagrams, and truth tables. Truth tables list all possible input combinations, one on each row. If there are n inputs, there will be 2 to the n combinations, or 2 to the n rows. So for the example where we have 2 inputs, A and B, there are 4 rows. If we have 3 inputs, A, B, and C, we have 2 to the 3rd combinations, or 8 rows. To ensure that you do not miss any input combinations, write the input combinations as if they were ascending binary. In this example, we have 0, 0, 0, 0, 0, 1 for 1, 0, 1, 0 for 2, 0, 1, 1 for 3, 1, 0, 0 for 4, 1, 0, 1 for 5, 1, 1, 0 for 6, and 1, 1, 1 for 7. 8 combinations going from 0 to 7. There are 6 basic gates: and, or, not, NAND, NOR, and XOR, sometimes referred to as exclusive OR. We'll look at each of them one at a time. The NOT gate is unique in that it's the only one that accepts one input. Like all gates, it has one output. The NOT gate inverts the input. So if we have a 0 going in, there'll be a 1 going out. If we have a 1 going in, we have a 0 going out. And we can see that in the truth table. 0 as our input, 1 as our output. If we have a 1 for our input, we'll have a 0 for our output. For the Boolean expression, we use a little tick symbol to denote a not. So that's A not, B not, C not. The symbol, the logic diagram symbol, is a triangle with a circle at the end of it. A goes into the triangle and comes out as X. For this course, and in the textbook, we will use the tick, the A not, to show A not. However, there are other ways to represent not, other notation schemes. So if you've already taken logic and are more familiar with a different notation scheme, please feel free to use it. The AND gate. The AND gate accepts 2 input signals. The AND gate is 0 unless both the inputs are 1. So looking at our truth table, we have a 1 as our output when both the inputs are 1. In all the other cases, the output is 0. We use a dot to signify the Boolean expression for AND. Think of it as multiplying. Anytime that we have a 0 as our input, our output is 0. 0 times anything is 0. The logic diagram that we use looks like a D. I like to think of it as AND. Looks like a D. The NAND gate. The NAND gate is the opposite output of an AND. If we look at the logic symbol, we see that we have the D shape for the AND, but at the end of it, we've got the NOT circle. The logic diagram for a NAND is a NOT and an AND. And it's the exact opposite for the truth table. We will have a 1 unless both inputs are 1. So if both inputs are 1, we have a 0. All the other times, we have an output of 1. And the way that we represent it as a Boolean expression is we put our AND in parentheses, and we have a NOT outside of it. A and B knotted, NAND. Comparing AND and NAND, again, they look very similar. The difference being the little circle at the end of the D for the AND gate. Our outputs are exactly opposite. An AND gate with 2 inputs is 0, 0, 0, 1. The output for a NAND gate is 1, 1, 1, 0. The OR gate. For the OR gate, we have an output of 1 unless all the inputs are 0. If all the inputs are 0, the output is 0. Otherwise, the output is 1. We represent the OR gate with a slightly curvy diagram, which I have a problem drawing myself. Looks a little bit like a sideways Star Trek Enterprise insignia. And for the Boolean expression, we use what we think of as the plus sign. A or B. The NOR gate. NOR gate has the opposite output of an OR gate. A NOR gate, if both inputs are 0, the output is 1. A NOR gate will have a 0 for the output in all other cases. The logic diagram for a NOR looks just like an OR, followed by our NOT symbol. So a NOR gate is a NOT OR. It takes the OR's output and negates it. For a Boolean expression, we write our OR inside a pair of parentheses, and we give it a NOT outside the parentheses. So a NOR Boolean expression is a NOT OR. The logic diagram is an OR followed by a little NOT symbol. And the truth table is the opposite of the OR. So comparing it again, the two symbols look similar. The major difference being the NOT at the end of the OR symbol. For the truth tables, they're exactly opposite. 0, 1, 1, 1. The NOR, 1, 0, 0, 0. One more gate. The exclusive OR, XOR. The exclusive OR will have an output of 1 only when there's just one input as a 1. Otherwise, the output is a 0. Let's look at the truth table. In rows 2 and 3, you see there's 1, 1. There's a single 1. And the output is 1. For the rows that have no 1s or have more than 1, 1, the output is 0. For an exclusive OR, the output is 1 when there's a single input as a 1. We represent the exclusive OR with an OR symbol and a little line in front of it. That's the symbol for exclusive OR. Our Boolean expression, we use an OR symbol inside of a circle. Looking at OR versus exclusive OR, the OR will have an output of 1 if any input is a 1. The exclusive OR will have a 1 as an output only when there's a single 1 in the input. Gates can be designed to accept more than 2 inputs. For this course, we will have a maximum of 3 inputs. The figures used in this video were taken from Chapter 4 of Dale and Lewis's Computer Science Illuminated, 7th edition. That's it for this video. If you have any questions, please let me know. Be well.